Lab mates. So today I was thinking that we can do another International Chemistry Olympiad problem, and this one I like it because it makes you think a bit, and it's not very, you need to know a couple of things, but you can work it out using your head. So the problem is T6 in 2019 International Chemistry Olympiad, and it's a study of polymers, and it's quite nice. So to the problem itself, we have this molecule and its spectrum, the hydrogen NMR spectrum shows this data, and the first question asks which hydrogens are doing which signals in the HNMR spectrum. So if you are feeling okay, try to do it in your own. And okay, I think you tried. I don't know if you really did, but anyways, I'm gonna get started to do some applied chemistry, and let's get it started. First of all, you can use a reference table to know which are the chemical shifts, usually from which functions, but I'm not using here because I did not tell you important information. This signal, the A, if you put the sample on D2 water, D2O, D2 heavy water, the signal disappears at all. Okay? So try again. I'm sorry on the past moment because this information was really important. So let's get started. Thinking in using this information, we can already know which hydrogens are from this signal, because think with me. The nitrogen have this pair of electrons that it can attack another molecules, and then these hydrogens can switch. So if we have this deuterium here, the nitrogen can attack it, and it gives the pair of electrons back to the oxygen, and then we can and then it can doing this eternally, because another molecules of the solvent can just, like OD minus came here and take this hydrogen and switch all these hydrogens. So this signal, this information that in heavy water it disappears, reveals that the hydrogens bounded to the nitrogen are doing that signal, because it's the only place on the molecule that it could happen, this change in hydrogens. Okay, then we know both of them are A. Both of them are A. Okay, now to the next one. Knowing that two hydrogens emit in the spectrum have an area of 0.6, and the area is proportional to the number of hydrogens, we know now that each hydrogen have an area of 0.3 on the spectrum. Then these 0.9 correspond to 3 hydrogens. If it corresponds to 3 hydrogens, then only could be that that place on our molecule only can be this little group there. Then B is here. These hydrogens. Okay, next one, C. 0.6, so 2 hydrogens. And which ones are? So 2 hydrogens there have a chemical ambient that is different from others. And the only place we can see on the molecule that shows that is these hydrogens that are bonded to a carbon that is bounded to a nitrogen, because it differs in electronegativity, polarize the bond differently than on oxygen bounded to a carbon, and this different polarization change the form that the carbon hydrogen bound is polarized to. Then the chemical shift is different, and then we can assume there is C, both of the hydrogens. If they are C, the rest of them is D. So D, 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 D. Okay? So we finished here. Let's get going. The second part of the problem, which I liked and is more interesting, express the average degree of polymerization N as a function of the area AOC2H4, which is this monomer of our polymer of the NMR peak of the repeating unit, and the area AOCH3, which is this methyl group, N group. Okay, and calculate N using this function. So let's do our function. First of all, let's think. Our area of the area of all the hydrogens, it's equal to the area of ACH2H4 plus the area of this CH2. Okay? Because every one of them are D. So we only want this one for our function, and let's calculate it sooner. And then AOC2H4 is gonna be equal to AD minus, to the other side, minus ACH2. Okay? Just change things around and we can calculate it now. AD is 133.7. You can see this on the table I made earlier. Okay, and this area of CH2 there are 2 hydrogens, so we can assume it's 0.6. 0.6. Then area of our monomer it's equal to 133.1. Okay, we are gonna use this on our function. Nice. I'm gonna use some space. I will not take off this molecule because it's very pretty. I don't know what you think about it. Comment below if you think this little polymer is a filthy beautiful polymer. Okay? That's creepy moment. Okay, let's get to the problem. So we can simply use proportion here, because if we have the area of CH3 of the methyl end group and it corresponds to 3 hydrogens, then our area of the monomer it's equal to 4 times N, because there are 4 hydrogens per monomer. So N times 4, it's the total number of hydrogens, okay? Nice. And then we can just multiply it. So in the end, it's going to be the area of our monomer times 3 equals to area of the methyl end group times 4N. Okay? Nice. And then just clean it up, and we can work all by isolating this one. So I'm sorry, we need to isolate the N, because we want to know the degree of polymerization. So N is equal to AOC2H4, which is the monomer area, times 3 over this thing. It's going to divide all this. So area of the methyl end group times 4. Okay, pretty basic. Now we just plug in our values, and N is going to be equal to the area of the monomer, which is 133.1, if you remember our calculations, times 3 over 0.9, which is the area of our methyl end group, times 4. If you do these little calculations, you get to the answer of 110.9, which is approximately 111. Okay, so Rn is equal to 111. So there are 111 little boys on this polymer boy. Nice? Nice. This was a fine little problem. Really nice. Everything just pretty. No, nothing really. Just make you think, but nothing really hard. Simple calculations. All thought. I like it very much. And that is that. Thank you if you watched it until now. And see you next time. And kisses. Mwah!